Good morning.
Flippin' Physics.
Let's derive the equation for the capacitance of a parallel plate capacitor. We have actually already derived two equations for two parallel infinitely large charged plates with equal magnitude but opposite sign. The first is that the electric field between the two plates is constant and has a value equal to the magnitude of the surface charge density on one of the plates divided by the electric permittivity of free space. Now, we know surface charge density equals the magnitude of the charge on one of the plates divided by the area of one of the plates. The other equation we derived is that the electric potential difference in a constant electric field equals the negative of the magnitude of the electric field times the distance d between the 2 points across which the electric potential difference is measured, and that distance is parallel to the direction of the electric field. In other words, the magnitude of the electric potential difference across the two plates of a parallel plate capacitor equals the electric field between the plates of the capacitor times the distance between the two plates. Bo, please use those equations to determine the equation for the capacitance of a parallel plate capacitor.
Sure. Don't we just substitute the equation for the constant electric field between the two plates to get an equation for the magnitude of the electric potential difference, which exists between the two plates of a parallel plate capacitor, and then substitute that into the equation for capacitance? The charge of the capacitor cancels out, and we get that the capacitance of a parallel plate capacitor equals the electric permittivity of free space times the area of one plate of the capacitor all over the distance between the plates, right?
That is correct, Bo.
Yep, but we still don't really know what the electric permittivity of free space is.
Well, you are about to find out. An important piece to realize about this equation for the capacitance of a parallel plate capacitor is that it assumes there is a vacuum between the two plates. Usually we place an insulating material between the plates of a capacitor. This is both to help physically separate the two plates and because it increases the capacitance of the capacitor. This insulating material is called a dielectric. The original electric field in the capacitor is in black in the illustration, and I have identified the original electric field as capital E0. When a dielectric is placed in that electric field, the electric field arranges the molecules in the dielectric according to the law of charges. The positive sides of the molecules in the dielectric material are attracted to the negative plate of the capacitor, and the negative sides of the molecules in the dielectric material are attracted to the positive plate of the capacitor. This polarizes the dielectric, and the polarized molecules in the dielectric induce an electric field opposite the direction of the original electric field E0. The induced electric field caused by the dielectric is in blue. The magnitude of the net electric field in the capacitor with the dielectric in it is then smaller than the original electric field. The net electric field typically has no subscript because it is the electric field which exists in the capacitor. Again, adding a dielectric reduces the electric field in the capacitor. And because the magnitude of the electric potential difference in the capacitor equals the electric field times distance between plates, the electric potential difference in the capacitor is also decreased when a dielectric is added. As long as the capacitor is isolated and not part of a closed electric circuit, adding a dielectric does not change the charge on the capacitor. Therefore, because capacitance equals charge divided by electric potential difference, adding a dielectric to a capacitor increases the capacitance of the capacitor. Now, the way we define the effect of a dielectric is with the dielectric constant. The symbol for the dielectric constant is the lowercase Greek letter kappa. It looks basically like a lowercase k. The dielectric constant equals the ratio of the electric permittivity of the dielectric to the electric permittivity of free space. That means the dielectric constant has no units. And electropermittivity is the measurement of how much a material is polarized when it is placed in an electric field.
Oh, right. That makes sense. That is exactly what happens to a dielectric when it gets placed in a capacitor. The dielectric gets polarized in the electric field of the capacitor, and the electropermittivity of the material is just a measurement of how much the material is able to be polarized.
Exactly, Billy. The easier it is for electrons to change configurations in a material, the larger the dielectric constant of that material. And sometimes the dielectric constant is called relative permittivity, But usually on the AP Physics exams, it is called the dielectric constant. Bobby, please use the equation we previously derived for the electric field between the two parallel plates when there is a vacuum between the plates to determine the dielectric constant in terms of electric fields.
Okay, well, we know the electric field between the parallel plates equals the surface charge density of one plate over vacuum permittivity. I think I get it. Okay, so that is the electric field between the parallel plates when there is nothing between the two plates. The electric field when there is a dielectric between the plates equals the surface charge density divided by the permittivity of the dielectric, which evidently has no subscript. The ratio of the vacuum electric field to the dielectric electric field then equals a fraction with those two equations in it. Surface charge density cancels out, and the permittivity of the dielectric over the electric permittivity of free space is what we are left with. And that equals the dielectric constant. So the dielectric constant equals the electric field with a vacuum divided by the electric field with a dielectric.
Correct, Bobby. However, the electric field with a vacuum between the plates is electric field naught, and the electric field with a dielectric between the plates is the electric field with no subscript. Billy, please now derive the equation which relates the capacitance with a dielectric to the capacitance with a vacuum between the parallel plates.
Absolutely. Let's start with the capacitance of a parallel plate capacitor, which equals the electric permittivity of free space times the area of the plate divided by the distance between the plates. And I guess we will call that capacitance naught because it is the capacitance with a vacuum between the plates. I guess we will call the capacitance with a dielectric just capital C with no subscript. And that equals the same equation as the one with the vacuum, only with the electric permittivity of the dielectric instead of the electric permittivity of free space. And because we know the dielectric constant equals the electric permittivity of the dielectric material divided by the electric permittivity of free space, we know the electric permittivity of the dielectric equals the dielectric constant times the electric permittivity of free space, which we can substitute into the equation for the capacitance with the dielectric. That means the capacitance of a parallel plate capacitor with a dielectric equals the dielectric constant times the permittivity of free space times the area of one plate, all divided by the distance between the two plates. Oh, and that means the capacitance with a dielectric equals the dielectric constant times the capacitance with a vacuum.
Yes, Billy, thanks. And thank you very much for learning with me today. I enjoy learning with you.